Okay, I'm going to do a couple problems from your homework. In this first particular problem, we have a rectangular crate that is on a incline of 35 degrees, and the surfaces have friction. We are given a coefficient of friction of 0.270, and we want to know what are the minimum force must be applied perpendicular to the crate, to the incline, to prevent the crate from sliding down. So we have this green arrow right here. We have the green arrow, which is some applied force. And that's coming down. Now, with the other forces, the normal force and the perpendicular force are going to cancel each other out without friction, or with friction, it doesn't matter. Our frictional vector is going to be in the opposite direction than the parallel force, which is going to be in the downward direction. So if we have a condition, for example, where the parallel force is equal to the frictional force, then the motion of the crate down the slope is zero. There's no acceleration. In this case, we are going to make an assumption that if we don't have that downward force, applied force right here, that this crate is going to go down the slope. Okay. And we can figure that out by simply as making F parallel is equal to negative mg sine 35 degrees, and the frictional force is equal to mu mg cosine 35 degrees. And we can calculate both of these and see what the difference is. The difference is about approximately 9 newtons. And I'm going to put a negative in front because it's going down. But we have a different situation here. We want to apply a force perpendicular to the slide that will stop the crate from sliding down. So let's figure out what that is. Well, first of all, let's take a survey of all the forces we have here. Our net force is going to be equal to, we have the parallel force plus the force caused by friction, and then we have another force. Okay, and this other force is a perpendicular force. Now, since this is a system that has friction in it, then we have to say, well, this friction is going to be a factor of this force. So the problem comes down now to solving for this F right here. So let's set up an equation so we can do that. So actually, these are all going to be equal to 0, but let's just start off with solving what this equation is going to be. So we know that F parallel is going to be equal to F of the friction if it's in equilibrium. But we don't have a case. We have some other force, okay? And this other force is the applied force that's perpendicular, okay? So we can go one step further and we could say the perpendicular force is going to be equal to mu F plus the frictional force by itself. We need to apply the mu here on this perpendicular force, and we'll call this applied force right here. We need to put that mu here because we do have friction on the surface. okay, and we also have the frictional surface. So in order for this box to stay stable and not move, this equation is true. The parallel force going downward must be equal to the frictional force plus the applied force. Okay. So let's write the equation out now. And so what we get is the parallel force is going to be equal to mu s Fa, which is the applied force, plus mg cosine 35 degrees. Okay, and we'll write this out. Now we'll write down what the F parallel is, and that's going to be mg, the sine of 35 degrees. We already got rid of the negative by putting it on the other side of the equal sign, so we're all set there. And this is going to be equal to mu static Fa, the applied force, plus mu, the static force, times mg cosine of 35 degrees. Okay, so all we need to do now is to solve for f of a. Okay. So in this case, f of a is going to be equal to mg sine 35 degrees divided by mu of s minus mg cosine 35 degrees. So all I did is solve for f of a here. So let's put in the numbers. Okay, so we have a mass of 2.6 kilograms times 9.8. I'm not going to put the units in for that. The sine of 35 degrees, all divided by 0.270 minus 2.6 kilograms, 9.8 times the cosine of 35 degrees. Oops. Okay, and so this is equal to the force, applied force coming down, and this comes out to 33.3 newtons. Okay, so let's go back and just kind of review what's happening right here. So we have a force, this green arrow is 33.3 newtons. And with that force, applied force, the crate is in equilibrium. Okay, so let's go on to another problem. Okay, in this problem, we have a system of masses on a pulley connected by a string or cable. Okay, and it tells us the coefficients of friction. It gives us the coefficient of static as 0.5 and the coefficient of kinetic as 0.3. So they must be wanting us to do two types of problems, one with static and one with kinetic. They give us our masses M1 and M2. So the first question is, what is the acceleration at rest? Now, the acceleration at rest, since this M2 is only 3.7, and this is a little over 10 kilograms, M1, the acceleration for this first problem is going to be 0. Okay, so we can answer this by saying the acceleration is going to be 0. Okay, what about number 2? Now, number 2 is a little different. So on number 2, how to figure this out, you have to take or look at each one of these masses and put in a free body diagram. Now you can just do one, as long as you understand what's happening to the other one. In this case, I'm going to do a free body diagram for M2, okay? So let's take a look at M2. And let's figure out what's going on with M2. Well, first of all, M2 has a vector going down, which is M2G. Okay, now what about the tension that's going in the opposite direction? Well, we know that we're going to have an acceleration going down, which will be a negative acceleration. But in terms of negative, that means this direction. As long as we understand it's downward. But we're going to have one vector is going to be the mass times that acceleration from M1. M1's going to be sliding across here, okay? And then the other vector is going to be caused by the friction of the surface of M1, okay? So that one is going to be mu M1 G. And we're going to use the coefficient here of 0.30 because we're in motion. Okay, so how do we solve this problem? Well, we have everything we need right here in the body diagram. Okay, so let's just put it together. First of all, we have M1A plus we have mu M1G, okay? And then also we have a negative M2G. So all these together must equal an acceleration, and the acceleration is on mass 2. So it must be equal to M2A. So now I just need to solve for the acceleration. So let's do that. So I'll take this in steps. We have M1A plus M2A is equal to M2G minus mu M1G. Okay, let's break it down one more time. The acceleration is going to be equal to G M2 minus mu M1 divided by the sum of the both of the masses. Okay. So now we just need to plug in these values. Let's do that. 9.8 meters per second squared. M2 is 3.7 kilograms minus 0.30, that is mu there. And we have mass 1 is 10.1, all divided by 3.7 plus 10.1 kilograms. Okay, so now we will get our acceleration. All right. So this comes out to A equals, let me erase that, sorry. A equals 0.476 meters per second squared. Okay. So as long as we had the negative here for M2A, we set up the equation this way. We're just solving for A. We know the direction is down by looking at this equation up here. And so that's our answer, 0.476 meters per second squared. Okay, hopefully that was helpful. These are similar to a couple of your homework problems. Thank you.